Hello students, welcome to the 10th lecture of the online course of Nanophotonics, Plasmonics and Metamaterials. Today we will be discussing matrix theory of dielectric layered media. So here is the lecture outline. We will have a quick recap of the Fresnel's equation, and then we will introduce a very effective theoretical tool called transfer matrix or T matrix method that can be used for calculation of reflection and transmission across any multi-layered medium. So in doing that, we will first learn how to obtain T matrix for an interface, then we will look for the T matrix for a layer, and then how to obtain a overall T matrix for a multi-layered system. We will try to correlate T matrix to reflection and transmission coefficients so that we are able to calculate reflection and transmission of any multi-layered system from T matrix, that we will see. And then we will take an example of a very popular optical device called Fabry-Perot interferometer, and we will obtain the T matrix for that device. We will show you how to do that calculation, and also we will obtain reflection and transmission coefficients and other important parameters for a Fabry-Perot cavity, that will be finesse and Q factor. So here is a quick recap of Fresnel's equation. So if you remember from the last few lectures, we have discussed about light falling on a particular interface between two different media. In that case, some portion of the light is getting reflected and some portion is getting transmitted. Now depending on the polarization state of the incident light, the amount of reflection or transmission will vary. Okay, so in the case of S polarized light, so if you remember that S polarization is basically, so the polarization where the electric field basically strikes out or it is perpendicular to the plane of incidence. Now when I say what is plane of incidence? Plane of incidence is basically that plane where the incident ray, the normal to the interface and the reflected ray, they all lie in one plane. Okay, so if you consider the incident wave propagating this way, okay, you can consider the electric field to be either striking out, that is S polarization, or it can be parallel to the plane of polarization. Okay, so in case for S polarized light, which is also known as T polarized light, okay, you can find out what is the reflection coefficient and transmission coefficient, that is R perpendicular and T perpendicular. On the other hand, for T polarization light or polarized light, which is also known as parallel polarization or TM polarization, okay, so you can find out what is R parallel and T parallel. And we have seen that in the case of normal incidence, that is when theta I equals 0, these equations basically become 1. So R parallel will become equal to R perpendicular, and that boils down to a very simple equation, that is N1 minus N2 over N1 plus N2. Okay, what is N1 N2? So N1 is the refractive index of the first medium, N2 is the refractive index of the second medium. We also can see that the transmission coefficient T parallel and T perpendicular will also become same, and they will become 2N1 over N1 plus N2. So with this understanding, we have to now approach with real life problems where there are multiple layered medium that we will encounter. In that case, how to use Fresnel's equation, okay, and that method is known as transfer matrix method. Always remember here Fresnel equations actually tell you the reflection and transmission from one particular interface. Okay, now let us take a general problem. So the general problem is of a wave propagation in and through a multi-layered structure. So the multi-layer structure can be regarded as an optical system where there is one input port and one output port, and the transfer matrix method will allow you to calculate the overall reflection from this multi-layered system and what is finally coming out of this. So in all this multi-layered, there are many interfaces that you will be encountering, like here. So if you consider this is your incident wave that is coming down with a wave vector of k and hitting this multi-layered structure, as you can see there is 1, 2, 3, 4, 5, 6 particular layers. Okay, so this particular layer, every layer will have a different interface, because this one, let's assume this structure is in air. So you have air and this particular material. So you have this as one interface. Then you have this material and this material. So this is another interface. Similarly, this is one interface, this is one interface, this is one interface, and so on. So there are many interfaces which are coming in one after another. Also, there are layers of different thickness, different material property. So how light wave is basically going through each of this interface and then layer, interface and then layer, all these things can be taken care of by the T matrix or transfer matrix. So let us see how it works. So let the normal to the interface plane. So this is the interface plane, as you can see. Okay, we assume that the normal to the all interface plane is basically x. Okay, and in that case the interface planes are basically parallel to yz, those are basically vertically out of this. Okay, you can see. And we have also defined different refractive index for different region. It means there are different material present at different positions. That is how the multi-layer structure has been made. So if you write that nx equals n naught, that is basically for the region when x is less than x naught. It means before x naught the material is always n0 or n naught. Okay. Then you can see that between x0 and x1, means in this region the material property is different. It is having a refractive index of n1. So this is basically nx. It means the permittivity of this multi-layer structure is a function of x and it is changing. Okay, and this is changing discretely in different steps, and this is how it is written. So between x1 and x2, as you can see here, it is given as n2, and then between xn minus 1 and x, okay, that is this one, you are basically having xn. Okay, or you can say that when x is greater than xn minus 1, that is when you are, you have crossed the multi-layer structure, or the light wave has crossed the multi-layer structure. What is the refractive index? It is able to see, that is small n, capital N. Okay, fine. So this is how you have defined all the refractive index for each of this medium. So you have to remember that there are two possibilities of the incident wave. It can be either a S wave, that is a TE wave. So in that case the electric field is either striking out or it is perpendicularly going in, as it is shown here. This is the wave vector. Okay, and it can be also P wave, that is parallel wave, or TM wave. In that case the electric field is actually parallel to this plane. So there are these two possibilities. So we can actually define the thickness of each of this layer. So you can call this thickness as a parameter d. So you can call di is basically xi plus 1 minus xi. So that's a general formula that will tell you about the thickness of each of these layers, and you can refer to each of these interfaces in a general form using, say, I and I plus 1. So one interface is formed between I and I plus 1. Okay, so that way you can generalize them. Now what happens in this case, that the normal to the interface plane, okay, and the wave vector, they define a particular plane, that is the incident plane. So what we have seen here. Okay, so that is this, in this case the incident plane is basically this screen. Okay, because that is the interface. The interface is basically perpendicular to this particular screen. So you will see that the wave vector is basically along this plane. We are assuming that. Okay, and in doing so we are also considering that kx component is 0. It means the wave vector will not have any y component. Okay, that's an assumption. Even if they have it, we can use transfer matrix method, but the calculation becomes little complicated. Okay. So, let us assume in this case that the wave is particularly lying in that plane. Okay. So, the wave vector is basically in xz plane, okay, that is this particular plane. Now, we will consider each of these cases T and Tm, okay, and we will be able to describe the electric field in terms of its amplitude, which is E, and E is a function of x, y and z. Now, in this structure each layer will have the contribution of forward propagating wave, okay, it means it is towards the increasing x, okay, and it will also have contributions from some reflection from the interface, okay. Similarly, it will also have backward propagating wave. As I told you, the reflections are considered as backward propagating wave. So, the total field that you can see in layer I can be given as, so this is the total field. So, total field is basically AF, that is the amplitude of the forward moving wave. So, the forward moving wave is moving towards plus x direction, okay, and it has also got a component along z, okay. So, it is AF e to the power minus j kxi x plus kz z plus AB. AB is the backward one, okay, backward propagating wave. So, you can write e to the power minus j. So, backward propagating wave will propagate along minus x direction. So, it will be minus kxi times x plus kz z, okay. And then when you break this exponential into two components, and then if you club these two together, you can write this as the forward electric field. So, this is the forward electric field, this is the backward electric field, or you can say forward propagating electric field or backward propagating electric field, okay. And what are these components? So, kxi is basically square root of ni k0 whole square minus kz square, okay. So, in this case I is nothing but all those different layers that you will be encountering. So, starting from 0, because if you remember here, the first layer, the incident medium is 0 and then the transmission medium is n. So, until that you will have all different wave vector in each of these layers, okay. So, I will range from 0, 1, 2 up to n. What is k naught? That is basically the free space wave vector given by omega by c. Now, do you understand this one? This is nothing but that the wave vector k naught will get modified in every layer which has got a refractive index of ni. So, it will become ni k naught, and ni k naught is nothing but, so you can write in vector form that ni k naught square is equal to the x component square plus y component square, okay. So, that way you actually get this. So, from that only you can obtain what is the x component. Now, here is the pictorial representation of what I was describing. So, in this case, let us take that you are talking about interface between Ni and Nj. So, there are two layers, okay. So, right now let us find out what is the transfer matrix for one interface. So, these are two layers Ni and Nj. So, there is a interface in between, okay, clear. So, this interface is at a position of xi, that is the position of the interface. Now, let us assume that you have, we will be writing the forward propagating waves and backward propagating waves in the two region. So, this is xi. So, anything before xi we will write as xi minus, and anything after this xi boundary we will write as xi plus. So, right now what we are doing, we are trying to correlate this, okay. So, let us first write, we will not look into the matrix equation first, let us write what is EF xi plus, that is, so whenever there is some incident wave, okay, that is forward propagating the forward direction, we will write it as EF, and then to mention the location we are saying it is xi minus. Now at this interface there will be some reflection. So reflection is a backward propagating wave, so we write it as EB. And what is the location? It is again behind the interface, so we will put Xi minus. Now there is some transmission, so that transmission part we write as EF Xi plus. Why Xi plus? Because it is on the other side of the interface. There could be another ray if there is like another source on the other side, but it is not the case. We are assuming that the source is only from one side, so this line can be disregarded. So in that case what you can write, okay, but if this is there, let's assume if it is there, what will be this called? This is basically a backward propagating electric field. The location is Xi plus. Clear? So now let us try to write down the equation for EF Xi plus, that is the forward propagating wave that is in this region. So this is nothing but you take this one, the forward propagating wave, and multiply with the transmittance. So whatever is the transmittance across this interface, we name it as Tij. So Tij times this one, okay. So that is one component. Another thing would be if there is a backward propagating wave here, some part will get reflected and that will also come here, right. So these two rays will be on the same direction. So the other component will be Rji. Why Ji not Ij? Because here the light is actually in region J and it is going towards I, so it is Rji, reflection from the interface while going from J to I. So it is Rji, and then you multiply EB Xi plus. Clear? So this is how you get this equation equals Tij EF Xi minus plus Rji EB Xi plus. Okay. Again, if you try to write what is this one, that is this particular wave. So how is this particular wave coming? So this particular wave is basically a reflection of this forward propagating wave, or it could be transmission of this particular backward propagating wave on the other side. So EB Xi minus can be written as Rij EF Xi minus, this one, plus Tji, that is this one, the transmission across this, times EB Xi plus. Clear? So this is how you are able to make a relationship between the forward and backward propagating waves on both sides. Now as you can see, they are bit Xi plus, Xi minus, they are mixed up. So if you try to do some algebra and try to rearrange the terms in such a way that you get all the left side fields in terms of the right side fields, that is how you can rearrange them. In that case, so if you have the right side fields, you multiply with a particular matrix, you will be able to get the left side field. So that way this becomes the transfer matrix of this particular interface. So how do you obtain this? This is very simple. You actually start with this and try to do the algebra to rearrange the terms, okay, nothing else. And here you also can use some other symmetry relation from the Fresnel equation, something like Rij will be equal to minus Rji, and there is another equality, so that is Tij times Tji minus Rij times Rji will be equal to 1. So if you use these two relations which are coming from Fresnel equation, you can easily verify this by yourselves. If you go to the first slide where I have shown the Fresnel equations, if you actually put the values here, you will be able to prove those relationships. Okay, fine. So after you do that, you can actually simplify this further, and this will get a very nice look. It looks like this. So all the left side fields, okay, the forward and the backward field, they look like 1 over Tij times 1 Rij, Rij1, this is the matrix, and then these are the right side fields. So forward and backward propagating, both the fields are there. Got it? So this is how you obtain the transfer matrix for an interface. Now, if you see here that what is Rij? Rij is nothing but the reflection coefficient, right, between the interface I and j. So, if you see here, what is the reflection coefficient? This is basically the ratio of this field over this field. So, you can write this over this, right, and Rij is already known to you from Fresnel coefficient. So, you can plug in those values here, which is Ni cos theta I minus Nj cos theta j over Ni cos theta I plus Nj cos theta j. Okay. Similarly, you can also write what is Tij. Tij will be Ef xi plus, that is the transmitted electric field over the incident electric field. Incident electric field is this one. So, you can also see that this is nothing but 1 plus Rij, and that takes this particular term when you put this value of Rij. Okay. Similarly, you can also do this exercise for P polarization or TM polarization. There the value of Rij, the ratio is still same, that only determines, but then the value here will be different. Similarly, Tij will also be different. So, this is finally the thing that you can obtain, because you have to talk in terms of Rij and Tij parameters. So, when you write the transfer matrix capital Tij for the wave propagation through an interface between layer I and j, this is how it looks like. So, this is the transfer matrix. Capital Tij will be 1 over small Tij, this is the transmission coefficient, and 1 Rij and then Rij 1. So, which value to choose depending on which polarization of the light you are incidenting, you can choose that value, and that will allow you to compute this. Clear? Now, this is what is happening in the interface, and after the light has actually crossed the interface, it is actually inside a particular layer. Now, depending on the material and the depth of the layer, there will be some changes in the phase being accumulated. Okay. So, let us see how do we actually make a matrix of a layer. So, the next step is to build a transfer matrix for wave propagation through a layer. So, let us consider that layer is I. In that case, the refractive index can be written as Ni. So, what are the waves here? So, this is the wave that has entered. Okay. So, it has basically come from this interface, right. So, we will call it as Ef xi minus 1, but it is on the other side. So, it is plus, fine. So, it goes like this, and this wave only will become the forward propagating wave of xi minus, because now if you see, this is another interface, this is the forward electric field, but this is on the left side of that interface. So, you can write Ef xi minus. Now, from here what happens, there will be some reflection. Okay. We do not forget about the transmission here, because that will give you the interface transfer matrix of the interface, but we are interested about the what is happening inside a particular layer. So, when you move this and hit this particular interface, you get some reflection. How do you name this reflection? Eb xi minus, backward propagating, and it is xi minus, and this field, when it will travel and reach here, it will be called as Eb xi minus 1 plus. Now, these two electric field, do you think they will be exactly same, or there will be a phase delay because of the path they are traveling from this point to this point? So, this is what will be the contribution of a particular layer. So, let us try to write them in terms of equation. So, you can write this equation that Ef xi minus is nothing but Ef xi minus 1 plus, then whatever the phase it has accumulated here. So, you have to look for the x component. So, you will e to the power minus j kxi di. Okay. And then this one also can be correlated, that this field Eb xi minus 1 plus can be Eb xi minus times this much amount of phase that is added, e to the power minus j kxi I di. Now what is di? Di is, as I mentioned before, di is nothing but the thickness of this layer of material Ni. So this is di, this thickness. Okay. Now we can write it in short form that the transfer matrix. So you can actually again do the same kind of maths and find out that the transfer matrix that correlates the left side's field with the right side field will be something like this one. So capital Ti will be e to the power j phi I 0 and 0 e to the power minus j phi I. Now what is phi I? Is nothing but kxi di, that is the amount of phase. So it is a very generic quantity or general like it is a in general a complex quantity, I must say, and in the case of a lossless medium and in the absence of total internal reflection, you will see that this phase is a real quantity. And how to calculate this phase? As I told, phi I is nothing but kxi di. So kxi can be written as 2 pi over lambda naught times Ni, right? And then you have to also look for the x component, it is a kx, right? So what is the kx? If this is the direction of wave propagation, what is this component? If this angle is theta I, it is cos theta I, right? So that is how cos theta I has actually come, and distance is di. So this is how you obtain it. So if you look into this particular equation, that also tells you one more important thing, that phi I is basically a phase change, but this phase change is not related to the amount of the path length AC. Okay. So it is not about from here to here. Okay. Because of the angle, you have seen that you are basically considering a 90-degree angle here, and this is a plane, this is another plane. So this phase difference is basically coming from the distance between these two planes, and this perpendicular plane to the wave vector is nothing but the phase front. So d or the phase change that you are calculating is basically coming from the difference in the phase front, that is AB prime. So that is the difference between the two phase fronts, and phi corresponds to that particular value of AB prime. Clear? So now we have got both the things ready. We know what is the transfer matrix for one interface between two different material, and we also know what is the transfer matrix for one particular layer. Okay, and then if you put them together, you can add them up, okay, or multiply, not add them up, you have to multiply them, okay, and that will give you an overall transfer matrix. So if you write the left side with respect to the right side quantities, then the transfer matrix is called T0 to n. If you remember, the first layer is 0, the last layer was n. So this matrix will also have 4 components, T11 or 4 elements, T12, T21 and T22. And how do you obtain this? You have to start with the first layer. So if you remember, if you go back, you will see that so this is one layer. So you will get a transfer matrix for this one, but this is the layer where the wave is already there, the wave is propagating in that medium, so you don't do anything for that. So what you first encounter is the interface between n0 and n1. So you have to got a transfer matrix for this one. Okay, then you have this particular layer, then you have this interface, then again you have this layer, and so on. Finally you will also have this interface and then this particular layer. So that many transfer matrices you have to put together and multiply, and that is how you will be able to get the overall transfer matrix, which is given as T0 to n. So it looks bit cumbersome and lengthy process, but you can use MATLAB codes for writing this transfer matrix, and you can do the matrix multiplication very easily, and that will give you the overall transfer matrix of a multi-layered system. Okay. So now let's look into how to obtain the overall transfer matrix. As I mentioned, that this expression can be used for solving a variety of wave propagation problem. So first thing, you will start with transfer matrix for that plane or that interface where the plane wave was propagating, and then it will encounter the first layer. So you have to put the transfer matrix for that interface. Okay. So first interface, then layer, then interface, then layer, and finally you will get another interface, and then it will enter into another layer, and that's it. That will be the overall transfer matrix. Now, as we mentioned earlier also, that we can assume that there is no field that is coming from the right side. That means EB n minus x n minus 1 plus is always 0. There is no electric field from the other direction. So once you do that, you can simplify the equation like this. EF x0 minus EB x0 minus can be correlated by the transfer matrix. This is the overall transfer matrix. That is why look at the superscript 0 to n, and these are the elements of the matrix 1 1 1 2 2 1 and 2 2, and here we have put that this term is 0. Okay. So EB x n minus 1 plus is 0. Clear? So this is the final transfer matrix. Now, will you be able to correlate the reflection and transmission from this transfer matrix? The answer is yes. Now, if you see, this is the forward propagating wave, that was basically the incident wave. What is EB x0 minus? That is the reflected wave from the very first interface. So if you want to get reflection coefficient, it will be nothing but the ratio of EB x0 minus over EF x0 minus. And if you talk in terms of the matrix elements which you have just computed, you will compute this matrix, right, by multiplying all the matrices. You can actually get this ratio by doing T0 to n. You have to look for the 2 1 element, this one, and divide it by the 1 1 element. Then this will give you the reflection coefficient. What about transmission? The transmission coefficient is nothing but this over the incident one. So EF xn minus 1 plus divided by EF x0 minus. Okay, and that can be simplified, and you can, from the equation you can see that it is simply 1 over T11. Okay, so the main important part is to calculate this transfer matrix. Once you are done with the calculation, you have got the 4 elements, you can find out what is the reflection coefficient, what is the transmission coefficient. And once you know the reflection and transmission coefficient, reflectance and transmittance are very easy to find. Reflectance will be nothing but modulus square of your reflection coefficient. Transmittance will be nothing but real of nn cos theta n over real of n0, that is the incident media, times cos theta 0. This ratio will be multiplying the modulus of transmission coefficient square. Very simple. And always remember, if it is a non-absorbing media, capital R plus capital T should be equal to 1. Okay. So that completes the discussion on transfer matrix. So this transfer matrix will allow you to find out reflection or transmission from any multi-layered system, and it's a very effective tool. Lot of researchers even today use transfer matrix method for calculating reflection and transmission from multi-layered systems. One such multi-layered system is Fabry-Perot interferometer cavity, or also called as Etalon. So you might have heard of this Fabry-Perot interferometer before. So it actually tells you that it's an optical resonator. So you have optical, or you can say light rays entering here, okay, and there will be some reflection obviously. So say this is the light ray incidenting, okay, then you have got some reflection, it has entered after being refracted into this medium. So this is n prime, this medium is n, and again this is n prime, the same old medium. So you can take air, glass, air to easily understand. Okay. So this wave has entered, hit this interface, some part got reflected, then remaining part got transmitted. This transmitted light, when it hits this particular interface, again some part got reflected, okay, and remaining will get transmitted. Out of this reflection, when it will hit this particular interface, again some part will get reflected, remaining will get transmitted, and it will go on happening. Okay. So in that case, what you will see, if all these reflected lights, if all these lights which are basically coming out of this, they constructively interfere, you will get a particular color. Similarly, so these are all, you can say, because these are all back in the same direction, you can say all these are basically reflected light. All these are on the other side of the incident wave, you can say these are all transmitted light. Okay. So you can say that when all of them will interfere constructively, you will get a color out there. Okay. So this is how typically a Etalon or Fabry-Perot interferometer works. So this is again a multi-layered structure, one dielectric, another dielectric, and then third dielectric. So this is a 3-layer system, 1, 2 and 3. How many interfaces are there? 2. This is the interface between first and second layer. This is the interface between second and third layer. Okay, this is the interface, right? So it's a 3-layer system. So now we have to first write what is the transfer matrix for T12, this particular interface. So this is the formula we can bring from those lessons we have learned today, that for a particular interface, this is how it looks like. Okay. Now R12 and R12 you can write as R. Okay. T12 you can calculate and find out what it is. Where you will get this from again? These are the Fresnel coefficient. Okay. So you can simply do the Fresnel coefficients and calculate and put them here. What about capital T23? That is basically the transfer matrix for this particular interface, that is given as this. So here R and here this will be minus R, because these are the same media, just opposite. Okay. So it was air to glass, here it is glass to air. So you can put minus R here. So as it is also shown that R is nothing but R12, which is minus R23. Or if you don't like this kind of short simplified relations, blindly take the Fresnel's equation and put the parameters, you will get the equations. So you have got the 2 transfer matrices. What is left? The only thing left is the transfer matrix in layer 2, that we name as T2. Okay, fine. So see, it is only written 2, not IJ format. Layer 2, so it is only 2. So e to the power j phi 0, e to the power minus j phi. Okay. Now your job is to put the value of phi here. So you can also take this one common and make it look like this. So phi is nothing but 2 pi lambda naught, that is k naught, times n, that is the refractive index, times L, that is the thickness, and it is basically the x component, so cos theta. So this is the value. So now you have got all the 3 matrices, T12, T23 and also capital T2, this is the layer 1. So the overall transfer matrix is nothing but, you can name it as 1, 3. It is like 0, n. Okay. So that is nothing but T, that is multiplication of all this transfer matrix. So you put all the elements and multiply them. Okay. And after you multiply them, you will get the 4 components. Once you got the 4 components, your reflection coefficient will be, again you go back to this formula, reflection coefficient will be nothing but 2 1 element divided by 1 1 element, and transmission coefficient will be 1 over the 1 1 element. Okay, that is what. So that is very simple. So let us see. Yeah, T21 over T12, these are the 2 elements. So from this matrix, after multiplication, whatever you have got, you pick those 2, 2 1 and 1 1, you have put them here. So this becomes your reflection coefficient, and T will be like this 1 over T11. So, you put all these values here, this is what you get, very simple. So, this is how you can get the reflection and transmission coefficient. Obviously, it is easy to find out what is the reflectance and transmittance as I mentioned. So, it will be square of the reflection coefficient, also square of the transmission coefficient. Here the final medium and initial medium are same, so that ratio will be 1. Okay, clear? Now, why this is important? This particular Fabry-Perot interferometer has got a lot of application. Even in laser cavity you have Fabry-Perot interferometer. So, here what is happening? So, if the incident intensity is taken as unity, the first transmitted intensity, this one will have the values of T12, that is the transmission here, okay, and then whatever you are getting here is T12 times whatever is the transmission coefficient of this interface, that is T23. So, this value becomes T12 times T23. Similarly, that if you look for the reflection condition, the second one, this one will get twice reflected. So, it is getting a reflection from here. So, it will have R23, also it will have multiplied by R12. On top of that, you will have the coefficients of T12 and T23 to find out what is coming out here. So, they will become progressively weaker, as you can understand, and if you are able to maintain the phase difference, okay, in that case they will add up constructively and you will get a particular color. So, the phase difference is nothing but delta phi, phase difference is given by delta, that is taken as round trip phase difference. So, it is given as 2 phi. So, phi you already know how, what is the formula, you put 2 phi here, and then you can understand that if this round trip phase difference is an integral multiple of pi. So, if it is equal to m pi, then you are able to get a constructive interference and your transmission will be maximum at those particular points, okay, or you can say at those particular angle theta. So, in that case you can also find out what will be the maximum transmission. But in the other case, if you take when the round trip phase difference is basically odd multiple of or you can say 2m minus 1 times pi, okay, in that case you can find out it's odd multiple of pi by 2. In that case it will give a minima in the transmission, because in that case all these waves will destructively interfere, okay. So, that is how you are able to, Fabry-Perot is able to do the filtering. So, only at certain wavelength you will get very sharp transmission, other wavelengths will be blocked, okay. So, these are the conditions, and if you try to relate it to wavelength, so lambda is nothing but c by f or c by nu, okay. So, you can find out the condition for maximal transmission as nu m, m is an integer, nu or f it is fine. So, it will be c over 2nl cos theta. So, this will tell you that the choice of theta, n and l will tell you which frequency you will be let out of this particular interferometer. So, it actually becomes like a filter, Fabry-Perot cavity based filter, okay. So, with that you can also find out that all transmitted contributions, they at resonance they will interfere constructively, but in off resonance the contributions do not go longer, they will no longer interfere constructively. In that case the two neighboring resonance frequencies will be separated by so called spectral range, free spectral range, FSR. So, that is given as delta nu, which is nothing but nu m plus 1 minus nu m. So, if you do the calculation, you will see it turns out to be c over 2nl cos theta. That means how much the two resonant frequencies will be different to each other, okay. So, that also tells you that how much channel spacing you can obtain from that particular filter. There is another parameter that is called fineness, or you can say fineness, how fine it is. Okay. So, it is directly related to the mirror's reflection at each interface. Why mirror? Because every reflecting surface is a mirror, right. So, in it alone also you have seen that there are two, ideally Fabry-Perot cavity that is used in laser, they will have very good reflector in one end, and in another one it will be like 99.95 kind of reflectance. So, they are very good mirror to give you very good spectral selectivity. So, this mirror reflection plays a important role. So, the fineness factor is given as pi square root of r over 1 minus r. So, you can see the higher the mirror's reflection at each interface, higher is the fineness, it means the sharper will be the transmission peak. So, sharper peak means you will get very good quality output, filtered output. Another important thing that will also correlate, so I already gave out the hint that when it is very fine, you also will get very high quality factor, and quality factor Q is defined as omega r, that is the resonant frequency divided by the spread in frequency, okay, that is delta omega. So, delta omega is nothing but FWHM, full width half maxima, okay. So, it actually gives you a measure of the resonance in the spectrum, fine. So, this is how it looks like. So, if you take r equals 30, so you will get this solid line. So, you see they are not that fine, not that sharp. So, you still have transmission, but it is not that selective. So, on the other side, so this is basically transmission spectrum. So, at this particular cases where the phase is 4 times pi or 5 times pi or 6 times pi, it means every m pi, okay, you see there is a resonance, fine, and this is transmission resonance. It means if you look into the reflection spectrum or capital R, which is nothing but modulus of small r square, you will see that there is drop. So, reflection based, it is basically band stop filters, but in the case of transmission, you can actually get band pass filters based on Fabry-Perot cavity. So, here the cavity length is actually taken care of by this one. So, 5 pi that actually gives you an idea of what will be the cavity length, because this value is changing, fine. So, you can actually correlate with that, but always remember that the resonating peaks will appear at phi equals pi by phi will appear at m pi locations, where m is an integer, fine. So, with that we will conclude our discussion today on T matrix. As I mentioned, it is a very useful tool for theoretical calculation of reflection and transmission across any multi-layer system. This one was an example of a multi-layer system. It is called Fabry-Perot interferometer or Etalon. Okay, it is a 3-layer system. You can do it for any layer system, 4, 5, 6, 7, 8, 9, 10, 11, or even up to 200 layer system, does not matter. The same formula of using the transfer matrix for the interface layer, multiply everything, you will get a transfer matrix with only 4 elements, okay. And then if you take the ratio of 2 1 over 1 1, you get reflection coefficient. If you take the inverse of the 1 1 element, you get transmission coefficient. Once you have both this coefficient, you take the square of it, okay, modulus square of it, and for transmittance you have to add that factor, you get reflection and transmission. That is it, very simple. So, with that we'll stop here today, and in the next lecture we'll start the discussion of 1D photonic crystals. Thank you.